And now you should see a screen in full screen mode, I think.
Yeah, everything works fine.
Yes. Yeah, right. Wonderful. Thanks a lot for confirming. So yeah, thank you so much for the introduction. It is a great pleasure to be here in this conference, and I'd like to thank first the organizer for giving me the opportunity of being here today and for having the opportunity of listening to so many amazing talks. So today I'm going to tell you about how you can use graphene and magnetic van der Waals heterostructures to engineer new forms of quantum matter. The idea of this talk relies on something that we have been exploiting in condensed matter and in quantum materials for quite so many years, which is the notion that if we combine the right elements together, we may be able to engineer new forms of quantum matter and new forms of quantum behavior. And I mean, of course, we have, let's say, amazing examples of this in the cold atoms community, where we can engineer new lattices and even engineer interactions with lasers. We also have examples of this in the atomic scale physics community, where quantum materials can be assembled atom by atom. And what I want to tell you today is that we can do something similar with two-dimensional materials, and in particular, we can engineer new types of quantum behavior by combining the right two-dimensional materials together. So the basic idea is that when you take two different two-dimensional materials, let's say graphene, for example, and you put them on top of another, you essentially get something that's called a Moire pattern. And with this Moire pattern, you can get new emergent physics associated new length scale. And of course, the idea is that even though at the beginning, most of the experiment focused on graphene, in principle, in the next few years, we can start exploiting this very same phenomenology with other different types of two-dimensional materials, including insulators, semiconductors, superconductors, ferromagnets, quantum spin Hall insulators, and even quantum spin liquids. And just to give you a simple example of what is the power or the possibilities that we can have with this, let me just highlight the case of twisted bilayer graphene, which is the simplest twisted van der Waals heterostructure. And the basic idea is that just by taking two layers of graphene with a small angle between them, and by putting the right interlayer biases, you can realize a huge family of correlated states of matter, including superconductivity, topological networks, strange metal Chern insulators, correlated insulators, quasi-crystalline physics, and so forth. And this is just in a material that has just carbon atoms. So now you think about all the different two-dimensional materials that we have, well, it is kind of easy to think that the possibilities are huge. And I mean, of course, from the point of view of a condensed matter theorist and quantum materials engineering, this is almost a dream come true, meaning that if we combine the right two-dimensional materials, we may be able to create new forms of quantum matter that we were not able to observe in conventional materials. So we can think that we can create new forms of topological insulators, new forms of, let's say, unconventional superconductors, and perhaps even new forms of fractional quantum matter. So the reason why this is working and the reason why we are capable of doing this with two-dimensional actually fairly simple. And it reflects the fact that just by controlling the angle between two different two-dimensional materials and by applying an interlayer bias, we are capable of controlling simultaneously the strength of electronic interaction and the fine details of the electronic dispersion. So in other words, we are capable of more or less engineering different types of with tailored interactions. So today what I want to tell you is that there's a third ingredient that we can try to exploit, which is two-dimensional magnetic materials. And in particular, with these two-dimensional magnetic materials, we will be capable of controlling the internal quantum degrees of freedom, and ideally to get a higher flexibility to engineering quantum matter. So from the materials point of view, today I'm going to focus on these four different materials. Essentially, they semiconductors, a two-dimensional metal, and by combining them in the right way, taking the right angles, taking the right interlayer biases, I'll show you how we can create new forms of quantum matter. And before going into the physics part, let me just first highlight that what I'm going to tell you today was only possible because of the work of a lot of people that are not today here presenting. And in particular, I'd like to thank Tobias, Annie, and Odette for the first story that I'm going to tell you today. Aline for prediction of heavy fermions in dimensional materials, and finally the atomic scale physics group at Aalto University, William Chaboulinou, Peter, Wanse, Somesh, and Mohammed for the perhaps the most remarkable story that I'm going to tell you today, which is the realization of heavy fermion phenomena in a twisted van der Waals heterostructure. So let me start with the first part of what I want to tell you today, which is how we can use traditional magnetic materials to create engineer correlated state of matter in twisted van der Waals systems. And this story is thanks to Tobias, Gianni, and Odette. So the basic idea is that since we have, let's say, different, lattices and electronic dispersions and interactions, we can start dreaming about realizing correlated states that we already observed in conventional compounds. And perhaps one of the first examples that we can think about is quantum spin liquids, which are these two-dimensional quantum states of matter that appear when we have local magnetic moments located in a lattice and with frustrated interactions. So this is, of course, a huge field that has been studied already for quite some time. So to be concrete, let me just say that today what I'm going to try to show you is how you can create a quantum spin liquid, dimensional material, but where your quantum degree of freedom is no longer the typical spin, but actually the valid degree of freedom that appears intrinsically in graphene. So the basic idea is that we are going to take a two-dimensional graphene bilayer, encapsulate it between ferromagnetic insulator, and in this system we will show how we can create a tunable quantum spin liquid state where the spin liquid happens in the valid degree of freedom of graphene. So from the microscopic point of view, actually fairly simple at the single part. So we essentially take an atomistic model considering several thousands of atoms in our unit cell. We include kinetic energy for the electrons, exchange proximity effect between graphene and the ferromagnets, and then Weierstrass spin orbit coupling that is induced by the ferromagnets. And we are going to work in a regime that is close to the magic angle, but not exactly at the magic angle, and in particular, the angle that we are going to consider 1.3 degrees. So we take our full atomistic model, we solve it, and we get that you see on the right top. And then with this bond structure that it's computed with a full atomistic model, we are capable of deriving a low energy model in an effective triangular lattice, which is the plot that you see in the right bottom. So the basic idea is that just by combining this twisted graphene bilayer with ferromagnetic insulators, we are capable of creating an effective model in the triangular lattice whose low energy physics is just controlled by two different parameters, and perhaps most importantly, where the spin degree of freedom has been fully lifted, and the only remaining degree of freedom that this system has is the valid degree of freedom. So now with this single orbital model in the triangular lattice, we include interactions, and then once we include interactions, we know that in the strong coupling limit, this model is going to map to an isotropic Heisenberg model. And in particular, we are capable of deriving all the different constants that control this valid Heisenberg model in the triangular lattice. And in particular, what is especially interesting from this system is that once you have this low energy electronic structure, just by applying a small electric bias, you are capable of changing very teeny details of the electronic dispersion. And in particular, with applying an electric bias, you are capable of controlling every single one of the exchange constants of your single particle model in the triangular lattice. So with this, you essentially know that with a twisted graphene bilayer encapsulated between ferromagnetic insulators, we can create a frustrated model with tunable interactions. And I mean, of course, solving a quantum spin liquid model, it's highly non-trivial, but the bottom line is that since you can control all the exchange constants here, one could look for this regime experimentally. So that was the first example of how we can exploit two-dimensional ferromagnets to create new states of matter. And now let me move on to perhaps the most, let's say, novel part of the talk, which is how we can use this notion of magnetism in twisted van der Waals materials to engineer heavy fermion phenomena. So just as a recap, or as a, let's say, brief introduction, let me just remind you what are heavy fermion physics. So heavy fermions are essentially a correlated quantum many-body state of matter that appears in especially heavy rare earth compounds, meaning compounds that have F electrons. the interest of this correlated state of matter is that we have extremely exotic forms of quantum criticality and conventional superconductivity and even topological superconductivity that appear because of this heavy fermion behavior. So the question is how we can do this with twisted two-dimensional materials. So from the, let's say, recipe point of view, the way of creating heavy fermions is actually not so exotic. So in short, we essentially need two different ingredients. We need a lattice of localized magnetic moments, and then we need a two-dimensional dispersive gas. And if we combine these two ingredients together on the right footing, having the right Kondo exchange and the right exchange constant between our magnetic impurities, we essentially push the system to a quantum macroscopic entangled state in which every single magnetic moment is by the dispersed gas, and this is what it's called the heavy fermion regime, and this is the parent state of the colossal mass enhancement that we have in heavy fermions, the different forms of quantum criticality and unconventional superconductivity. So this is essentially what we are going to do with these twisted two-dimensional materials. So, and now let me tell you of the first example of how we can do this, which is in twisted trilayer graphene. And let me again emphasize that this work was only possible because of Aline. So the basic idea is that we are going to take a twisted graphene trilayer, in particular with the top and bottom layers aligned and the layer in the middle misaligned, and we are going to compute the electronic structure of this and see if we have the right ingredients for heavy fermion behavior. So again, we are going to consider a full atomistic model with several thousand atoms in the unit cell. We solve it, we apply a certain electric field, and at the very end, what we actually observe is that the low energy properties of this system are described by the coexistence of localized modes and dispersive modes. And now the idea is that these localized modes, in the presence of interactions, can give rise to local magnetic moments, and the dispersive modes realize the two-dimensional dispersive electron gas that we were expecting. So now, perhaps the most important thing is to see if this system allows us to go in the right regime for heavy fermion physics, and to do that we essentially solve this model at the mean field level. We extract what are the Kondo couplings between the local moments and the dispersive electron gas and the exchange coupling between the localized moments, and essentially what we observe is that we can completely tune what is the ratio between the two constants just with the interlayer bias. So in other words, twisted graphene trilayer realizes a system that it's a tunable heavy fermion system, because we can essentially go through all the ratios between the two exchange constants. And just to put it in some words that are perhaps more common for the heavy fermion community, essentially we can explore the whole Doniak phase diagram of a heavy fermion compound in twisted trilayer graphene. Now let me move on to the most, let's say, important part of the talk, which is the experimental realization of a heavy fermion system in a twisted dicalcogenide heterostructure. And again, this experiment was, of course, only possible because of the wonderful work of the experimental group at Aalto University. So again, the basic idea is that to get a heavy fermion system, we need to combine a system that has a lattice of magnetic moments and a two-dimensional electron gas. So in particular, if one looks at the family of two-dimensional materials, one can find that there's a two-dimensional compound called 1T tantalum sulfide that realizes a lattice of local magnetic moments. And then there's another compound that is 1H tantalum sulfide that realizes a two-dimensional electron gas. So essentially, the experimental group drew this heterostructure. So 1T on top of 1H, and in this system, you essentially have the coexistence of the lattice of magnetic moments coming from the 1T phase and the two-dimensional electron gas coming from the 1H. So this is, of course, at the theory level, right? And now perhaps the question is, what should we see in the experiment to be sure that we actually fell on the heavy fermion regime? So to answer this, let me just give you a crash course on this heavy fermion phenomena, which is the following. So one of the simplest features that we can see in a heavy fermion compound is the appearance of a heavy fermion gap at half filling. And the basic idea is that when you are in the right regime between Kondo coupling and exchange coupling, essentially your Kondo sites can be replaced by Pseudo-Fermions, so fractional spinons, and your conductive electron gas remains a conductive electron gas, And the condo coupling essentially couples your pseudo-fermions coming from the condo sites with your conductive electron gas. And in short, what happens is that you get a gap opening at the Fermi level. So a system that originally is a metal, it becomes an insulator because of this condo coupling. So from the experimental, then once we know this, we pretty much know what to look at. So the idea is that if this system realizes a heavy fermion compound, we should see first condo physics on when we probe T lattice, and second, a gap opening when we probe the two-dimensional electron gas. So, we group those two different heterostructures, and then when we probe the 1T lattice, which is the lattice that has a local magnetic moments, we essentially see a condo peak. And then when we grow the opposite heterostructure, so with the 1H on top, we go with the STM, and we see the appearance of a heavy fermion gap. And just to mention, let me just emphasize that we looked at the magnetic field dependencies and temperature dependencies, and all the phenomena that we observe is compatible with the heavy fermion phenomena that is known in rare earth systems. So this is everything that I wanted to show you at the physics side. And then in the last minute, let me just mention what you could do if you wanted to test some of these theoretical calculations on your side. So, I mean, of course, from a theory point of view, we need to program at some point, we write a random model, we need to solve them. But at some point, if you just want to see a result, perhaps it is useful to have a tool that you can readily use. So for that, we essentially developed a code that is called Quantum Lattice that essentially allows you to solve different type anti-models just by pressing buttons and putting numbers in a user interface. And to show you how it works, it is perhaps most useful that I show you a video. So here I'm showing you how you can just open the interface and just create a certain system. You can select the type of lattice that you have. You can add different terms to the Hamiltonian like magnetism, spin orbit coupling, charge order, superconductivity, and so forth. And then once you are happy with your Hamiltonian, you press different buttons so you can compute different properties such as band structure, density of states, chair number, different types of topological invariants, different types of spectral functions, having interactions at the mean field level, and so forth. And essentially, this is everything that I wanted to tell you today. So if I may ask you to remember something, please remember that magnetic twisted van der Waals materials provide a very interesting platform to engineer a new family of correlated states, even this new form of quantum matter called heavy fermion physics. Thank you so much for your attention, and I look forward to your questions.
So thank you very much for your clear, nice presentation. Thank you for being in time. And the talk is open for discussion. And so are there questions in the audience? A very specific question. Isn't the 1T titanium sulfide 2-phase a spin liquid?
Yes, that's a very interesting question. The answer is that there are some signatures of quantum spin liquids behavior in 1T. But I mean, of course, identifying with 100% accuracy a quantum spin liquid is a very challenging task. So the bottom line is that having a quantum spin liquid, it is not actually bad for heavy fermion phenomena. So you can have a two-dimensional system that's a quantum spin liquid, you put it on a metal, and you can still get a heavy fermion system. So this is a very interesting question, but even if it is or if it is not, this doesn't affect, let's say, the emergence of heavy fermion physics.
Hello. Yeah, you showed this dispersion between this magnetic moment and this conduction band, and there is a gap, and how it is different with this normal band insulator. So it's like you are saying this condo insulator. So what's the difference between this band insulator and here the condo insulator at the half linear?
Mm-hmm. Yeah. So that's a very good point also. So the main difference is that in a condo insulator, that flat band that you have there is not an electronic flat band, but it's actually a spin-on flat band, meaning that that flat band is made of, let's say, fractional excitation that have spin but no charge. So essentially you have hybridization between an electronic band and a band that has spin but no charge.
Okay, but you said that you can also describe with this what did you say? It's the fermion. So it's
Yes, they are called pseudo-fermions. So the idea is that, let's say, they have fermionic statistics because they have spin 1/2, but they have zero charge. So those are essentially the fundamental excitations when you are in the screened regime in a condo system at hub filling.
Okay, thank you.
Thank you.